These are the general steps for how to draw any given atomic orbital. So step 1 involves finding the number of radial nodes the orbital has, and this can be found via the formula n minus L minus 1. Step 2 involves finding the angular nodes. Keep in mind that nulls will use the term angular node and nodal plane interchangeably, but they mean the exact same thing. And this is very simple because the number of angular nodes just equals the angular quantum number L. So whatever L is, that's the number of angular nodes you'll have. And just for a quick review, S is going to be a quantum number 0, P is going to be 1, D is 2, F is 3. Step 3 is really only applicable to orbitals that have orientation, aka they have a magnetic quantum number above 0. So this basically just means P, D, and F shells, does not include S subshells. And the subscript, so when you see P subscript X, that X is going to just represent the orientation. So what this means for us when drawing the orbital is that you need to define an X, Y, or Z, or multiple if need be, coordinate plane or arrow just showing direction. And then from there, you draw the corresponding angular node perpendicular to that direction. So this is going to make a bit more sense when we get to the examples, but just keep in mind that the angular node must be drawn perpendicular to the defined arrow. And then step 4 just involves shading the nodes differently whenever they cross a node. So whether that's angular or radial, as long as it crosses that node, that no-go zone, they have to switch colors, meaning they switch the sign of the math value. So let's go through the examples that nulls used in class, and hopefully it'll make more sense. Starting with the example 2px, the principal quantum number is n equals 2, and then the angular momentum quantum number is represented by the letter P, which means that the L equals 1. And then calculating the radial node, we get 2 minus 1 minus 1 equals 0. And again, angular node equals the angular momentum quantum number, which is 1. So that just means that in total we have 1 angular node and no radial nodes. So before I start drawing my actual orbitals, I need to first define the direction, because again, this orbital has a subscript x, and that means it has an orientation. So here I draw a vertical line, or vertical arrow, and label it the x-axis. Then I draw my angular node perpendicular to this axis I just defined. You could draw a horizontal arrow, it doesn't really matter as long as you keep the angular node perpendicular to whatever you draw. After I draw my axis and define it, and draw the node, then I'm going to draw my 2 shapes across the node, remembering to shade one of them to differentiate the change in sign across the node. Again, what this graphical representation means is just the probability density of the electron, aka how likely are you going to find an electron in these spaces, with the node representing a place where the electron physically cannot be found. If you look up the Orbitron, you can see some really cool 3D representations of the exact things that we are drawing. And that could maybe help you visualize what's going on a little better, so I would highly recommend giving that a shot. But here is a picture I pulled from the Orbitron, and the bottom right is just the 3D representation of the 2px orbital we just drew. So hopefully this kind of gives you a better idea of what's actually going on in 3D space. So now that we understand how to draw an angular node, let's do a radial node to kind of compare the two. So for 2s orbital, I do the exact same thing I did before. N equals 2, L equals 0. Number of radial nodes equals 2 minus 0 minus 1 equals 1. Number of angular nodes is 0 because my angular quantum number is 0. So in total, I have 1 radial node and no angular nodes this time, which is the opposite of the previous example. So if angular nodes are planar, meaning it's represented in our 2D space via a flat line, radial nodes differ because they're represented by a circle. So I draw a dotted circle to represent my one radio node. Note that I wrote angular node when I labeled it, but I meant to write radial, so that is just a typo on my end. Then I shade the region outside of the angular node to show how the sign changed from inside to outside the node. If we look again at the orbitron, this gives you a much better idea of what 2s actually looks like in 3D space. You can see there's a spherical empty space between the gray area and the blue area, and this empty space essentially represents the radio node. It's where the electrons physically cannot exist. Let's do a slightly more complicated example now, 3px. So same thing as before, n equals 3, L equals 1, number of radio nodes equals 3 minus 1, which equals 1, and the number of angular nodes is 1. So in total, we have one radio and one angular node this time. So the question is, how do these interact? Well, first, let's just start simple, define the x-axis, and then we draw the one angular node perpendicular to that axis. We draw our initial shapes across the angular node. So in our review session, someone asked, why do we need to have those two extra shapes adjacent to these inner shapes? And the reason for that is because of the existence of the radio node. When we pass through this radio node, we have to change shading again, which results in this outer shape. If we don't draw this shape, you'll notice that it just looks exactly like the 2px orbital. And obviously 3px can't be 2px. They're different orbitals, meaning that the shapes that we draw should also be different. So hopefully that clears up the confusion you guys were having. If it doesn't, feel free to just shoot me a message on Teams. The basic takeaway though is just that if there's a node, there must be a change in sign across the node, and that's what's kind of resulting in this shape on either side of a given node. Again, if we look at the orbitron, this makes a lot more sense in 3D space. So the final example is 4dxy. This time we have two orientation, but still just do the same exact things as before. N equals 4, L equals 2, number of radio nodes equals 4 minus 2 minus 1, which equals 1. Number of angular nodes is 2. So in total, I have one radial node and two angular nodes this time. So first, as always, we define our axes. This time though, we need to define both the x and y. I arbitrarily chose x as the vertical axis and y as the horizontal axis, but again, it doesn't matter much as long as you draw the nodes correctly in relation. So here I draw the angular nodes perpendicular to their respective axes. It's hard to see because it overlaps with the axis I drew as a directional reference, but it is the dotted blue and red line there. And then I draw in my four shapes with alternative shading that results from the two intersecting nodal planes. So that's why it results in four shapes, because there's two planes intersecting here. So there's these four planes of places electrons cannot be. But don't forget that we also have the one radio node, so we're not done yet. So next I draw the radio node kind of just encircling the first four shapes we have. And since we must have different shading across this radio node, just like any other node, we draw some more bumps that protrude on the other side of the radio node for each of the four previous shapes. Again, here's the orbitron if you want to see it in 3D space. Hope this helps.